Welcome to Engineering Simple. In this video, I'll go through an example of power factor correction with a motor. So using basically a motor as a load and also using that motor to correct the power factor. So this would be a good example to practice for the FE or PE exam. Because typically when we talk about power factor correction, we talk about capacitor banks. So in this example, let's assume we have two balanced loads connected to three-phase 480 volt feeder. Loads connected to a three-phase 480 volt feeder. So load 1 draws 70 kilowatt with a power factor of 0.80 lag or lagging. Load 2 draws 70 kVA with a power factor of 0.65 leading power factor. Load 2 is a synchronous motor. With the capability of correcting the power factor. So basically this motor has the capability of correcting power factor. So basically it can correct the power factor if needed. So let's assume P2, which is the real power or active power of load 2, will change negligibly. As Q2 changes. To correct the power factor. Changes to correct the power factor. Now the question is, determine Q2, we can call new, basically the new reactive power associated with load 2, which is a synchronous motor, that will correct the power factor to, this is the power factor of the system, to 0.90 lagging And I would recommend watching other videos that I made that go through power triangle and also lagging and leading, what they mean. So now, how do we set up this problem? So if we assume we have a problem like this on the FE or P exam, how do we tackle this problem? So solution or answer. So first of all, what is the initial load? Initial means prior to power factor correction. Well, we have a source, and we have a load. I can call L1 load 1. Then we have load 2, which I can call L2. They're kind of connected in parallel. This source will provide some complex power S, and total current will flow is I. Load 1 will consume S1, so the current would be I1. Then I2 would flow through L2, which would have a complex power of S2. So if you note here, S is equal to S1 plus S2. Because notice, I is equal to I1 plus I2, and obviously you have kind of same voltage since they're connected to the same bus, but that's not the purpose of this exercise. So load 1, if we go back to the problem statement, it draws 70 kilowatt with a power factor, I call it power factor 1, is equal to 80% or 0.80 lagging. So power factor 1 equal to 0.8. That means the angle theta 1, if I call it theta 1, is the inverse cosine of the power factor, which is 36.87 degrees. And notice it's positive because it's lagging. And again, the power triangle, so here's theta 1 is equal to 36.87 degrees. I know P1 is equal to 70 kilowatt. I don't know Q, I don't know S, but I can calculate them. So cosine theta is also, or theta 1, is equal to power factor 1. So cosine is the adjacent, which is P1. So adjacent side by the hypotenuse, which is magnitude of S. So magnitude of S is equal to P1 divided by power factor 1, which is 70 kilowatt divided by 0.80, which is 87.5 kVA. Q1, again, if I do trig, sine, I can do sine theta or tan theta 1. So tangent is the opposite. So Q1 divided by the adjacent side, which is P1. So Q1 is equal to P1 times 10 theta 1. Theta 1 is 36.87 degrees. So and P1 is 70 kilowatt. So if I plug in the numbers, I get 52.5 kilovar or kvar. So that's load 1. So I have all the information on load 1 now. Now I can do the same thing for load 2. So load 2, we said it draws 70 kVA with power factor, I'll call it power factor 2 of 0.65, leading this. So theta 2 is the inverse cosine of the power factor, which is 0.65. Since it's leading, so there's a negative sign, which is negative 49.46 degrees. So again, if I draw the power triangle, so I have P2, I have Q2, and I have theta 2, which is negative 49.46 degrees, and I have S2. And S2 is 70 kVA. So obviously this is one way you can draw. Since I put negative here, it's obvious that the power factor is leading. But obviously if you want to draw it the other way, you can do this. So this is P2, this is S2, this is Q2, and obviously the angle is this way, 49.46 degrees, but obviously it's negative. So you can draw it however you want, as long as you're consistent and you keep in mind that the power factor is leading. So that's why I'm showing a negative sign here. So cosine theta 2 is equal to P2 divided by S2. That means P2 is equal to cosine theta 2 times S2. That means P2 is equal, cosine 2 is a power factor, so 0.65 times 70 kVA, which gives me 45.5 kilowatt. As I did for load 1, Q2 is P2 times 10 of theta 2, which would be P2 is 45.5 kilowatt, theta 2 is negative 49.46. So if you plug in the numbers, you get negative 53.2 kvar or kilovar. So you see how I started from the problem statement. Now I drew a sketch of initial load. Then I calculated the information of load 1, basically the P1, Q1. I did the same thing for load 2. Now I'm still dealing with initial load. So I just want to keep that in mind. So if I do in terms of, so load 1, so P1 is 70 kilowatt and Q1 is 52.5 kilobar. Obviously I calculated, so basically you would just go here. Theta 1 is 36.87 degrees. What I'm trying to do here is, you have this sketch here, S, the total complex power is S1 due to load 1 plus S2 due to load 2. That's what I'm doing here. So here is the power triangle for load 1, and here's a power triangle for load 2, because load 2 has a leading power factor. I think it's 49.46 degrees, and P2 I calculated as 45.5 kilowatt, and Q2 I calculated as minus 53.2 kvar. So this is equal to S, which if you sum up, so P basically is 70 plus 45.5, which is 115.5 kilowatt, and Q is 52.5 plus minus 53.2, which is equal to minus 0.7 kvar. What I'm doing here is, this has P1 plus JQ1, that's load 1, plus P2 plus JQ2. So this is really equal to P1 plus P2. So that's what I'm doing here. I summed up the active power plus J times Q1 plus Q2. And that's what I did here. That's really what I did. In other words, the total P is P1 plus P2. And total Q is Q1 plus Q2. And as I showed on the power triangle, P1 is 70 and P2 is 45.5, which comes to be 115.5 kilowatt. Q1 is 52.5 plus Q2 is minus 53.2 kvar or kilowatt, which equals minus 0.7 kvar. So that's really what I'm doing here. So obviously here, so you can write S is equal to S1 plus S2, which is equal to the total P plus J times the total Q, which is 115.5 plus minus 0.7 J times 0.7 kvar. So just keep in mind this is in kVA. So the angle here, we can call it initial is the inverse tan of Q divided by P, which is inverse tan of minus 0.7 divided by 115.5, which comes to negative 0.347 degrees. And if you calculate the cosine, or the power factor, it's cosine of minus 0.347 degrees, which is cosine of negative. Negative is still the same as cosine of a positive number, which is 0.999, which is leading. But what we want to do is we want to correct this power factor, or the power factor of the source or system, to 0.9, lagging rather than leading. So now, like we did for the initial load, so the final or desired load we have load 1 doesn't change. We have 70 kilowatt and it has 52.5 kVAR. That's load 1, so this is load 1. Load 2 is a motor. It's a synchronous motor that has the capability of correcting the power factor. So, and we said the real part, or the active part, will not change. The change will be very negligible. So P2 will remain the same, 45.5. Where did I get 45? It's from here. So you see here is 45, or load 2, P2 is equal to, that's, so basically for load 2, since it can correct the power factor, this we said will stay the same, but the reactive power, this is what will change. So we want it to be lagging, so the new Q2, this is what we are trying to figure out. And obviously we'll have S2 new as well. And we'll have a new power factor angle as well. So what we want, so this is load 2, and we want this equal to some desired combined load. Basically, the real part will be 70 plus 45.5, which would be 115.5 kilowatt. And we'll have some Q, and we'll have some S total. But the angle, we said power factor, we want it to be 0.9 lagging. That means this theta nu, or theta 2 nu, we want, so it will be the inverse cosine of 0.90, which is 25.84 degrees. So this theta 2 nu is 25.84 degrees. So notice I have active power is known, angle is known. I can calculate Q, I can calculate S. So this Q here, we know tan of theta 2 nu is equal, so tan is equal to Q divided by P, which means Q is equal to P times tan theta nu. That means Q is equal to P, which is 115.5 kilowatt times tan of theta 2, which is 25.84 degrees. So if you carry out the calculation, you will get 55.93 kVAR or kilovar. So I know Q here. Obviously I can calculate S. And I know Q is equal to Q1 from load 1 plus Q2 from load 2. So what is Q2? Q2 is equal to Q minus Q1. Q is, I calculated 55.93 kVAR. So this 55.93 is due to the corrected power factor of 90% or 0.90 minus Q1, which is 52.5 kVAR. So this comes to 3.43 kVAR. So this is the new reactive power that the motor would have to supply in order to correct the power factor to a 90% lagging. So really using the power triangles is a powerful tool in solving power and power factor correction problems. So if you go through, you can see how I started from the problem statement. I started calculating the initial loads, load 1, load 2, then I kind of combined them to get the total load or the total power. Then I did the same thing for the final or desired load, basically the desired power factor. And from that, when I combined the load 1 and 2, I knew the power factor, I knew the real power. Obviously I can calculate the reactive power, and that reactive power is the reactive power due to load 1 plus reactive power due to load 2, which is what I'm trying to solve for. Then it just becomes a matter of simple algebra. So knowing how to manipulate or how to work with power triangles makes it a lot easier to solve any power factor problem. So that was it for this video. Thank you and have a great day.